As you can see from the title of this tutorial, this video is about what we call nomenclature and specifically binary ionic compounds. Nomenclature is a fancy word in chemistry for simply compound naming or formula writing. Nomenclature is very important. The reason being is we use a multitude of different chemicals in our everyday society. If you think about going to your pharmacy, right, the millions of different chemicals that you get there. If you go to the hospital, things that they will give you to try to remedy any problems. Right? Things that you put on your lawn, fertilizers, things that go in your car, gasoline. It is very important that everybody who is involved with using those things has a universal system for naming them and ascertaining their chemical formula. Because we cannot have one doctor saying that aspirin's formula is this, and a separate doctor saying, no, it's this. Whereas it happens that the other doctor who thought aspirin's formula was something could have been gasoline's formula instead. And that goes for all compounds. Whenever somebody says, oh, I'm working with lithium bicarbonate, it's important that everybody who is working with lithium bicarbonate thinks they're talking about the same thing. So that's why nomenclature is important. It gives everybody a common plane to operate on so we can have open lines of communication. A little bit of background of things that we will need to know when working with nomenclature. Right, the first is that we will find that we need to know charges of elements. And we talked about this before with the idea of cations and anions and how it links to the periodic table based on valence electrons. But I wanted to give a little refresher here. Certain groups carry certain charges from the periodic table. Not every group has a universal charge, but there are many. For instance, group 1 always carries a charge of +1. Now, the reason for that has to do with its electrons. For instance, if I took something from group 1 like sodium, if I had an atom of Na, there's its nucleus, first energy level has 2 electrons in it, 1s2, second level, 2s2, 2p6 would get us to 10 electrons, and then the third level is 3s1. And if you remember from the chapter where we were looking at the structure of atoms, you'll see that when something has 1 valence electron, it is very close to filling the octet rule by losing that electron. And when it loses that electron, it has 8 in its outermost shell now. The octet rule is complete. But when we lose electrons, we get charges. And we lose them, and it's positively charged. And because we lost 1 electron, it's a +1. So that's why group 1 carries a +1 charge. Other groups carry other charges. So let's take a look at what other groups will have. Group 1 is +1. Group 2 is +2. They have 2 valence. They tend to lose 2 valence. Group 13 has a +3. They have 3 valence. It's easier to lose 3 than to gain 5 to get to 8. Group 14 gets a little trickier. It has 4 valence electrons. So it's just as easy to lose 4 as it is to gain 4, to get to 0 or to 8. So this group will either be a +4 or a -4. 15 has 5 valence electrons, which means it's easier to gain 3 than lose 5. So it carries a -3. 16 is a -2. 17 -1. 18 is a 0. So then the question becomes, what about groups 3 through 12? Because we covered all the other groups on the table. Well, groups 3 through 12, known as the transition metals, get Roman numerals. that will tell you the charge on that atom. So if we were looking at a periodic table, group 1 all carry a +1. So if I say, what is the charge on rubidium? You'd say RB's in group 1, it's a +1. Group 2, get a +2. 13 gets 3, 14 gets 4, 15 gets -3, -2, -1, 0. And then anything in the middle here or here will have a Roman numeral telling you what its charge is. The reason being is that these elements, the transition metals, have the ability most often to carry multiple charges. Right? Sodium, for instance, is almost exclusively +1. So we don't need to know what else it would be because it's always +1. Something like copper, for instance, though, can be copper 1 or copper 2. Something like manganese, right, can be manganese 2, manganese 4. Right? So there's different charges. Iron can be +2 or +3. So because there are multiple charges that they can have, we have Roman numerals that tell us what particular charge we are working with for a transition metal. So I mentioned that these groups 3 through 12 get Roman numerals. So a quick refresher on what our Roman numerals look like. And we won't go too far down the list. We'll stop at, say, 7. Right, so the Roman numeral for 1 is just I, 2, II, 3, III, 4 gets a little different, IV, 5 is a V, 6, VI, and 7, VII. And for the most part, we will not work with many atoms that have more than a +7 charge. Right? So the Roman numeral 7 is about as high as we will have to go. So that's just a little bit of background information that we will need whenever we are trying to write the formulas or names of some different compounds that we'll work with. The latter half of this, like I said, is specifically focusing on binary ionic compounds. Right? So we're going to start that over here. And half of the battle in compound naming and formula writing is identification. How do we know we're working with a binary ionic? Well, if you look at the words, you can break some of it down. Binary, bi, is the prefix for 2. So the first thing you'll see is that it only has 2 elements. Ionic also tells us something. The types of things that are ionic are always a metal plus a non-metal. And because it's binary, we can't even have to worry about polyatomic ions. Because binary means there's only 2 elements, right? We can't have an ionic bond with a polyion with just 2 elements. Right? So, we will identify binary ionic compounds, right, by them only having 2 elements or seeing a metal plus a non-metal. Now, to show you why we're going to learn this system, I really quickly would like to show you basically the old way of figuring out compound formulas. For instance, if I knew I was forming a compound with calcium and iodine, right, which would be called calcium iodide, what we used to do was say, okay, calcium iodide is a metal with a non-metal, it's ionic. Right? We have to do a before and after picture. So you would say I've got calcium with 2 dots, I've got iodine with 7. Right? Iodine needs to gain 1, so it does, but calcium has 1 left, so we have another iodine come in. That gets transferred to there. And then in the after picture, you have a Ca plus 2, and then 2 different I's with now 8 dots that are both -1. And then from the picture, we'd say, oh, I need 1 calcium and 2 iodides. Its formula would be CaI2. Right? And that's effective, but it's rather cumbersome in terms of the drawn-out process. It would be nice if there was a faster way from going from the name of something to its formula. And the good news is that there is a way of doing that real quick. So what I'm going to list up here, right, is the way we write the formulas. Right? So every type of compound has 2 avenues. One where you're looking at the name of something and you want its formula, and then the reverse. You're looking at the formula and its name. So if I'm trying to write the formula for an ionic compound, I'm going to follow the following steps. Step 1, write symbol of each element with charge. So you write the symbol of each element with their charge, and you'll get those from the periodic table. Step 2. Cross charges down. And here, I'm going to add a little something that just says number only. As you can see from our list, our charges have pluses and minuses on them. We don't really care about those. What we really care about is the number. So we'll cross the numbers down and we omit the charges. Step 3. Reduce if possible. Right? So after you cross your charges down, you reduce those subscripts to the simplest ratio that they could possibly be. And if you follow those 3 steps, you should wind up with formulas that are accurate for what's going on. So if I went back and did the same thing that I did with calcium iodide and called it example 1, you would look at it and say, okay, calcium iodide, calcium is a metal to the left of the staircase. Iodine is a non-metal to the right of the staircase. That means it's an ionic compound. So we try to follow these steps. Write the symbol of each element with their charges. Calcium's symbol is Ca. Given the group that it's in group 2, and if you didn't remember, group 2 carries a +2 charge. Ca is a +2. Iodine has the symbol of I. It's in group 17, and what you'll learn is group 17 is a -1 charge. Right? So you did your symbols and charges. Step 2, cross the charges down in number only. So the 2 will go to the iodine, and the 1 will go to the calcium, and we don't worry about the charges. So when we do that, that leads us to Ca1I2. Right? We reduce it if possible. Right? 1 and 2 are as simple as it can get, so there's nothing to reduce. Right? And then lastly, I didn't add it here because we'll just get in the habit of doing it. We never write subscripts of 1. The fact that I have Ca written tells me I have at least 1 calcium. So we eliminate a subscript of 1, and sure enough, CaI2 matches what we got by doing it the long way. So personally, I think that this way is significantly faster by doing the symbols and charges and crossing them down. Let's take a look at another example. How about something like magnesium carbide? So magnesium carbide. Right, first thing we have to do is identify, is this a ionic or a covalent compound? Well, magnesium is here to the left of the staircase. Carbon, which is carbide, right, is to the right of the staircase. It's ionic. Then we're going to follow our steps. Write the symbol of each element with the charge. Magnesium symbol is Mg. It's in group 2, which means it's a +2 charge. Carbide symbol is C, carbon. And it's in group 14. And group 14 can either be plus or -4. So how do we decide what it's going to be? It's always the opposite of what the other thing is that it's with. So if magnesium's a +2, the carbon's going to be a -4 in this case. Step 2, cross charges down in number only. So the 2 will come down here, the 4 here, which would be Mg4C2. Reduce if possible. Well, this time 4 and 2 can be reduced. Those are both divisible by 2. And if I do that, I get Mg2C1. Right? And like I said, we never write subscripts of 1, so we just erase it. So the formula for magnesium carbide would be Mg2C. Taking a look at a couple more. How about we look at something like let's slide this so we can keep our rules up. We're going to look at something like iron 3 oxide. Now, when I look at the formula of this, it will say iron, III, oxide. Right? And the reason is going to become, well, why do we have a Roman numeral there? Well, go step by step and you're going to see why in a moment. Right? First thing we would do is decide, is it ionic or covalent? Iron lies to the left of the staircase. Oxide is oxygen. It's to the right. Metal, non-metal means we have an ionic compound. Step 1 of writing the formula says write the symbols with their charges. Right? So the symbol for iron is Fe. Well, if we take a look, Fe is right here. And we had no rule for group 8. Right? We learned that group 1 is +1, 2 is +2, 13 is 3, 14 is 4, 15 -3, -2, -1, 0. For all of these elements that are in the middle, you have to be given a Roman numeral that will tell you what its charge is. So because there is an III next to iron, that is telling you that it has a +3 charge. That's all they're there for, is to tell you the charge that you need that you can't tell by looking at the table. Oxide is talking about oxygen. It's in group 16. So it gets a -2 charge. Step 2 says cross the charges down, only in number. So if we do that, we get Fe2O3. Right? Reduce if possible. 2 and 3 are as simplified as they can get. Right? Erase subscripts of 1. There are none. So the compound iron 3 oxide, Fe2O3, right, would be just that. If you were curious, this compound gets a regular name too, a common name. That's what we know as rust. Iron 3 oxide is what happens to your bumper and whatnot when it gets rained on. Oxygen from the water or the air combined with the iron in an oxidation to form iron 3 oxide. Now, we get Roman numerals for the transition metals, but just like any rule, there are some exceptions. Right? So I'd like to put that in red and have you know that. Right? Exceptions to Roman numeral rule. Right? And there are some exceptions in both directions. Right? There are a couple elements that are in the Roman numeral section that don't get Roman numerals. And there are a couple elements that shouldn't get Roman numerals that do. Right? So let's go ahead and tackle the Roman numeral ones. Right? These are the following elements that do not get Roman numerals given with them, nor when we write their names will we give them. Silver, cadmium, and zinc. The reason being, the whole idea behind the Roman numeral system is that these elements can carry multiple charges, so we need a Roman numeral to tell us. Silver, cadmium, and zinc always possess the same charge, right? +1, +2, and +2 respectively. So because they always carry the same charge, it doesn't make sense to say silver I oxide, right? Because it's always going to be silver I oxide. It's never going to be something different. So they don't give Roman numerals, or you don't give Roman numerals to silver, cadmium, and zinc, even though those three elements, silver, cadmium, and zinc, fall in the transition metal section. On the reverse side, right, the following elements always get Roman numerals, even though they're not in the Roman numeral section. Tin and lead. Right? These will always get Roman numerals. Right? So even though tin is here and lead is here, and they are in not the transition metal section, they still get Roman numerals. The reason being, both tin and lead have the ability to be +2 or +4, and they can be multiple things, so they have to have a Roman numeral that know. So a couple exceptions, right? Do not give Roman numerals to silver, cadmium, and zinc. Do give Roman numerals to tin and lead as you go through. All right, so that's how we write the formula for these binary ionic compounds. I said that all of these were kind of like two sides of a coin, right? If we know how to write the formula, the other thing we'll have to do then is learn how to write the name. So we'll erase up what we have so far. And we will change this to writing the name. So if I'm writing the name, I am looking at a formula. So I'm going to list the steps if I'm looking at a formula to getting the name of that compound. Step 1. Write the name of the metal as seen on the periodic table, PT. Step 2. Write the root of the nonmetal with an IDE ending. Right? So if you remember, in all the names that we were seeing as we were writing formulas, it was always oxide, sulfide, carbide, iodide, bromide. Right? Ionic compounds always end in IDE. Step 3. Check if transition metal and determine Roman numeral. And next to this, I'm going to put two little subdivisions. Right? If we determine that it needs a Roman numeral, there's two things we try. The first thing we try is uncrossing the charges. And then the second thing we do is create a table that will allow us to figure out the Roman numeral. All right, so we'll leave those right there, and now we'll take a look at a couple different examples. First one. K2O. So if I'm looking at this, the first thing I need to decide is K2O ionic or covalent? Well, if we look, K is over here to the left of the staircase. O is over here to the right of the staircase. That means it's ionic. So we try to follow these rules, right? The name of the metal is seen on the table. K off the table is called potassium. Step 2, write the root of the nonmetal with an IDE ending. So the nonmetal off the table is oxygen. If we take the root of that, ox, with an IDE ending, that is where oxide comes from. How do we know where to cut it off? Usually it's after the first syllable, right? Bromide, iodide, fluoride. You usually take off, like if it's an IUM element, like barium, right? It would be baride, even though that doesn't happen. All right. If it's an INE, chlorine, fluorine, the INE goes and IDE comes in, but you'll get the hang of it. If you called that oxygenide at first, we'd be okay. All right, but you'll get the hang of how it goes. Right. Last but not least, check if the metal is a transition metal and then determine Roman numeral. So we were working with potassium. Potassium is in group 1. Right? Group 1 is not the transition metals. Remember, transition metals are groups 3 to 12. So because potassium is not a transition metal, right, that means we don't need a Roman numeral. We're done. The formula K2O gets named potassium oxide. What if we try something like Al2S3? Al2S3, no surprise, one to the left, one to the right, which makes it ionic. So I name the metal as seen on the table. Al is aluminum. I write the root of the nonmetal with an IDE ending. Sulfur is S, so take off the end, and you will get sulfide. And then lastly, if aluminum is a transition metal, we determine the Roman numeral. Right? Aluminum, it's close, group 13, but not in 3 through 12. So aluminum sulfide is good. Let's try something like ZnCl2. Again, these are all ionic because that's what we're talking about. I would name step 1, my metal is seen on the table, which is zinc. I would name the root of my nonmetal. Chlorine with an IDE becomes chloride. And then I check to see if zinc is a transition metal. Zinc is right here. It's in group 12, so it should get a Roman numeral, except, all right, there are 3 elements that do not get Roman numerals that we just talked about. And remember, zinc, cadmium, and silver, we think should get Roman numerals because they're in the section, but do not. So, zinc chloride is good the way it's written. Let's take a look at a couple where we do need to get a Roman numeral. How about something like HgSO4? F2. So, still an ionic compound. Hg lies to the left of the staircase, F lies to the right. So I write the name of my metal as seen on the table. Hg is mercury. F is the non-metal, so we need the root with an IDE ending, which is fluoride. Step 3. Check if my metal, which was mercury, is a transition metal. Is it in group 3 through 12? You bet. It's in group 12. Is it one of our exceptions? It is not. So that means this should get a Roman numeral. So the first thing we do to try to figure out what the Roman numeral should be is we uncross the charges. And what I mean by that is this. We're looking at HgF2. If I were to uncross those, it would put a 2 up here, and it's not written, but a 1 up there. The way we know that that works is if the charge on fluorine that we cross up matches what it should be on the periodic table, uncrossing will work. So fluorine is in group 17, and group 17 is supposed to be a -1 charge. Well, when I uncross it, sure enough, I get a 1 as my charge up there, and don't worry about sign. I get a 1. That means that the 2 that crossed up to mercury will also be correct. So we will put the Roman numeral for 2 in next to mercury. So you uncross the charges, and if the charge on the non-metal matches what it is off the table, right, then the charge that goes up to the metal will also be correct. That will work about 80% of the time. Right? 20% of the time, right, it will not work. All right? So we'll take a look at another one that does work, and then we will look at a couple that do not. So let's take a look at something like Cr2C. Let's sneak that in up here. So Cr2C, ionic, write the name of the metal as seen on the table. That is chromium. C is the nonmetal with an IDE ending, which makes it carbide. And then we say, is chromium a transition metal? And chromium is right here, so group 6 is in 3 to 12, so yes. Is it an exception? No. So the first thing we'll do is try uncrossing the charges. And if we do that, a 2 goes up to carbon, and a 1 goes up to chromium. Right? So if carbon's charge from the table is a 2, then we're good. We would just put a 1 in for chromium. Right? But take a look. Carbon is here. It's in group 14. Carbon's not 2. It's supposed to be 4. So that means uncrossing won't work. Anytime that happens, we go to this step. You create a table. And what I mean by that is this. If we get rid of what we just did, and I say Cr2C, we create a table by breaking it in half. Always start on the right side, because that's where you know the charge. I have 1 carbon. Carbon can be plus or minus 4. So it'll be a -4. Okay? Because 1 times the -4 gives us a -4 from the right. The whole compound is chargeless, which means this whole side has to add up to +4 so that they cancel. I have 2 chromiums, and I want to know the charge on chromium. So 2 times X has to be +4. Well, X has to be equal to +2. So chromium would have to be a 2. Right? Now I'll do a couple of these just because I know they're the most rare, but they tend to cause people the most trouble. Right, let's try something like VO3. VO3, ionic. All right, so I name my metal, which is vanadium. Root of the nonmetal with an IDE, oxa. Is it a transition metal? Vanadium is here. Group 5 is a transition metal, not one of our exceptions. Right, so first thing I try is uncrossing. That puts a 3 on vanadium and a 1 on oxygen. Oxygen is not supposed to be 1, it's supposed to be 2, which means uncrossing won't work. So we're going to have to do this again. Write the formula, break it in half. Take how many O's you have, which is 3, times the charge. We know O should be -2, and you get the charge from the right side. The charge from the left always has to be equal and opposite, so we need a +6. I have 1 vanadium times its charge, so what does its charge have to be to get us a +6? X has to be +6, so vanadium will be VI. And that's how you write the formulas, the names rather, of ionic compounds when given the formula. So I hope this helped you out if you're having confusion with binary ionic compounds, but as always, if it didn't, please feel free to come in for some help.